point of this video is to be able to determine the pH and the pOH and the concentration of hydroniums and hydroxides respectively for strong bases and for weak bases, and to be able to recognize strong bases and weak bases. Let's first start with our strong bases. Now, strong bases are things like sodium hydroxide, right? Barium hydroxide, strontium hydroxide, KOH, LiOH, basically anything that's a group 1 hydroxide, so alkaline metal hydroxide. For the alkaline earth, there's only really two of them that are considered strong, okay? And they are barium hydroxide and strontium hydroxide. And the reason why these guys are the strong ones is because of solubility. They have large KSPs, which means if you dump a bunch of them into the water, they're going to completely dissolve, unless, obviously, they're saturated, in which case you're still, at that point, you're going to have a pH that's above 14 and a pOH that's negative. All right, so those guys are readily dissolvable. Now, other bases will react, and will react completely, but initially, by themselves, okay, they're going to have a much less alkaline pH. For example, if we're dealing with magnesium hydroxide, which while it is an alkaline earth metal in there, is a relatively weak base because the KSP is 5.6 times 10 to the minus 12. And when this guy disassociates, as it will, you get this equation down here, which we've done before. We're really just doing a KSP problem, right? Now, make sure we're clear. If we add acid, we can cause this to dissolve more. We can cause it to shift to the right, and more it will dissolve, right? The solubility increase. Because essentially, if we add an acid, we're adding H pluses, and that will basically precipitate out the hydroxides as water. But assuming we just have a solution that's neutral water and magnesium hydroxide, we can determine the pH of that solution by doing some KSP tricks and figuring out what the hydroxide ion concentration is. So, some math right now. I lost my space. I thought I had more space. So your KSP is 5.6 times 10 to the minus 12, right? So, and your KSP is going to be equal to, right, the concentration of magnesium times the concentration of the hydroxide, right, to the second power. Now, since this has a 1 and this is a 2 here, we can assume that this is x and this is 2x, and so we're back to the same old KSP problem where we have 5.6 times 10 to the minus 12 equals 4x cubed. This is 2x squared, right? So we have 4, and then we can just divide by 4 and take the cube root, and when we do that, we get x value that is equal to 1.12 times 10 to the minus 4. Now, that's not the hydroxide concentration. That's the molar solubility, but it's also the concentration of magnesium ions, right? But we're not really interested in the magnesium ions, okay? But we're really interested in the hydroxides. And the hydroxide, the OH concentration, is equal to 2x. So that's equal to 2.24 times 10 to the minus 4. So that's our hydroxide concentration. And now we're back to the usual really simple problem, right? We can negative log this value. If we negative log that will give us the pOH. Now, we know when we have a pOH value where we have a lot of hydroxides, right, we should get a pOH value that's closer to 1. This is not particularly basic. So our pOH value here, when we do this and we negative log this number, we get 3.65, which means our pH is going to be 14 minus that number, which, teacher blanking, is, I hope I'm doing this right, yeah, 10.35 is our pH. And we can also obviously figure out our hydronium concentration. It's basic, but it's not strongly basic, okay? Now, by the way, that whole problem assumed one thing which I should have mentioned, which is that the solution was saturated, which is not tough to do because this is a relatively insoluble ionic compound, which means if you put half a teaspoon in a glass of water, it would be saturated. So obviously we could start with a lower concentration in which you completely dissolve and have to do the problem that way. But I don't think we're going to see that, so I'm not so concerned about that. Let me go to the next thing, a weak base. Now, most of our weak bases that you're going to deal with are nitrogenous bases. All right, and we have to, at this point, we're switching from Arrhenius, who basically says, Arrhenius, which is the earliest definition of a base, is a base is anything that makes a solution which the only negative ion is a hydroxide. All right, Bronsted-Lowry is much more inclusive. And the key thing here is focusing on nitrogen spaces, things that look like ammonia or have a group on there that is like ammonia. For example, this is methylamine. So ammonia, I'm going to write to the side here, is NH3, right? The structure looks like this with the 3 hydrogens, right? And with the 2 dots up there. This is methylamine. So this, instead of NH3, it's got the NH2, but still got those 2 dots. And those 2 dots there have the capacity to grab, okay, a hydronium. And when they do that, when they act as a hydrogen acceptor, they're going to behave as a base, right? So this is our methylamine right here on the left. And what we can see is the methylamine is basically acting as a hydrogen acceptor. So it's going from N with 2 H's on this side to an N with 3 H's and the positive charge, okay, on it. And so this is a base, and this is the this HB. This is the base. This is our conjugate acid, right? And the water, which is behaving as an acid on the side, is turning into hydroxides, right? And that's our conjugate base on that side. Now the Kb for this thing is 4.38 times 10 to the minus 4. And what that indicates is that the equilibrium lies pretty much to the left-hand side. This is a weak base, okay? Right, so the hydroxide is a much stronger base than methylamine, right? And Hb, which is this stuff here, okay, is a much stronger acid than water is, all right? All right, so now we're going to do the problem. Now, all these problems work out the same way. It's a very similar math to what we're dealing with acids. Just make sure you understand which species go where and what they actually are. So the bottom line is this. You're going to put the base, which is this thing right here, on the bottom here. Now, I'm not going to draw out the form. I could draw it in as CH3 and H2 if I want. That's what it is down there. And on the top, I would have the hydroxide, which I'm going to put in. And I could draw in CH3, NH3+, but I want you to see a pattern here, okay? And I think that's much more important, okay? Every single time you're doing this, you're going to see the exact same thing. You're going to have the base on the bottom, which is usually neutral, it doesn't have to be, a hydroxide, and you're going to have the conjugate acid with a positive charge here, okay, from the hydronium it picked up. And the assumption is, just as we did before, that there's a 1-to-1 relationship with these two guys. And if we do the solution, right, the critical thing is we're going to directly get the POH of the hydroxide, not the hydronium, because we're using this is a Kb. The Kb will always have the exact same format. Base on the bottom, hydroxide on the top, and conjugate acid on the top. We can assume that these two guys right here, right, these two guys are equal to each other, so we're going to assume we're going to do the same math here. We're going to do like, okay, the B on the bottom is 0.200 molar minus X, right? It's like we're doing an ice table sideways here, right? And on the top, we're going to have, this is X, and this is X. And we're again going to assume that this is less than 5%, and we'll check it at the end to see that it is, right? So we basically said X squared over 0.200 equals the value we're given, which is 4.38 times 10 to the minus 4. Now, this is a close one, but it actually works. When you solve for X in this case, you get X is equal to 0.0925. Now, if you put that over right, now that is equal to your hydroxide concentration, right? So we could take the negative log of that, and if we take the negative log 0.0925, that gives us a POH of 1.03, which is very basic because that's our POH, and our pH is equal to 12.97. And to check the 5% rule, because again, we're doing, this is more like a, to do that, we're doing approximately equal to, right? We can put that over so we put the 0.200, and on the top we put the 0.0925, times that by 100, and we get 4.6%. So it's close to 5%, but we're not breaking the 5% rule, so we can assume this is an acceptable assumption, and we don't have to break out the quadratic formula. And again, I'm emphasizing on the AP exam, my assumption is, and from what I'm reading on different websites, is that they're not giving questions in which you have to use the quadratic formula. Of course, you're more than capable of plugging this whole thing into your calculator and it will give you the roots, and you can do it that way, and you'll get a more accurate answer. So I don't see why you wouldn't want to do that. Just be aware on the multiple choice, this type of thing does show up when it's doable and the math is relatively easy.